Hi everyone. Today we're going to be talking about electric fields. Electric fields are a way of thinking about electric charges that helps us to understand how they will affect other charges. We can see here a pair of parallel plates. Now the way parallel plates works is that one of the plates will be set up with a positive charge and the other with a negative charge, and this will create an electric field. So what exactly is an electric field? Well, in physics, whenever an object attracts another object at a distance without touching it, then we say that the object is surrounded by a field, right? This is true of a number of different fields in physics. We can talk about magnetic fields, which is the area where something can be attracted by a magnet. We can talk about gravitational fields, where something will be attracted by gravity. Or we can talk about electric fields, where things can be attracted by electric charges. So the Earth will attract us with gravity, so we say it has a gravitational field. The gravitational field happens to look something like this diagram. Charged particles are said to have an electric field, and there are some charged particles which will have an electric field that looks like this as well. Now, electric fields have both magnitude and direction, which means they're not a scalar. The quantities are determined by the force that a positive charge would experience inside the field, right? So we can call this a vector field. If we put a positive charge inside this electric field that we can see in the diagram, it'll be attracted toward the negatively charged plate. That means that the direction of the negative field is downwards towards that plate. We draw field lines to represent the field, which we can see in this diagram over here. They're just straight lines with arrows on them. Now, a positive charge repels positive charges, yeah? That means that the field lines near a positive charge point away from the charge. We can see that in this diagram over here. We have a positive charge in the center, and the electric field lines point away from it. If we put a positive charge near the first one, it will move in the direction indicated by the field lines. Now, a negative charge does quite the opposite. It attracts positive charges, which means that if ever we look at the field lines around a negative charge, they will always be pointing towards that charge, right? Now, stronger fields are represented by closer together field lines, and we can see from these diagrams over here that the closer we get to the particle, the closer together the field lines get, which means that the electric field is getting stronger close to the particle. Algebraically, we represent electric fields with a capital E, right? Don't confuse it with energy, which uses the same symbol. Now, their strength is measured in newtons per coulomb. We'll learn why in a little while. The thing is, we don't have to use newtons per coulomb. We can also measure it in volts per meter. It turns out that if you go into the definition of a volt and the definition of a coulomb, then these units, volts per meter and newtons per coulomb, will be exactly equivalent. No matter which way you look at it, 1 newton per coulomb is exactly the same thing as 1 volt per meter, simply because of how newtons, coulombs, volts, and meters are defined. So the units are exactly equivalent, and we can use them interchangeably. Now, what about the direction of the force? Well, we've touched on this before. It turns out that we can use an equation, a very simple one, to figure out how much force acts on a particle that's in an electric field. Force equals Q times E. So Q is the number of coulombs on the electric charge, and E is the strength of the electric field in newtons per coulomb. So if we take newtons per coulomb and multiply it by a measure of coulombs, we end up with newtons. Now, if Q is positive, that means the direction of the force will be the same as the direction of the field. Remember that force and field are both vector quantities. So if we have a positive charge, like in the top of the diagram, and the field points to the right, then the force will also point to the right. If, on the other hand, we have a negative charge, like in the bottom of the diagram, the direction of the force, F, will be negative the direction of the field. And so if the electric field points right, the force on the negative charge will point left. So that's the end of the theory. We've learned a bit about electric fields in this section. Let's go on to some questions, shall we? Question 11. Draw an arrow to indicate the direction of the force on this particle due to the electric field. Now we have a positive charge. What does that mean about the direction of the force? Is it in the same direction or the opposite direction as the field lines? That's right, it's the same direction. We always draw electric field lines based on what the positive charge will do. Question 12. Draw the electric field in this situation. We have two positive charges and one negative charge. Now we know that the field lines of the electric field will point away from the positive charges and towards the negative charges. So drawing lots of arrows pointing into the negative charge and lots of arrows pointing away from the positive charges might give us something like this. So your answer should look something similar to this picture. We can see that the positive charges always have electric field lines pointing away from them, and the negative electric charge always has field lines pointing towards it. Question 13. If an electric field has a strength of 200 newtons per coulomb, what is the strength of the electric field in volts per meter? Now this is something like a trick question. It's asking you to compare volts per meter to newtons per coulomb. But as I've mentioned before, these two ways of measuring the electric field strength are exactly equivalent. So the strength of the electric field in volts per meter is also exactly 200 volts per meter. The units volt per meter and newton per coulomb are equivalent. They mean exactly the same thing. Question 14. A uniform electric field points from right to left. Two electrons are placed next to each other in the field, so one is on the left and one is on the right. Compare the strength and direction of the force on the electrons due to the uniform field. So we can ignore the force due to each other. Alright, so let's think about this. We have the electric field pointing right to left in this direction, and we have two electrons. Now, how do we determine the strength of the force on the electrons? Well, we use this equation, F equals QE. Right? Remember that one? Now, the charge on each electron is going to be exactly the same. So Q is constant. The E on each electron is going to be uniform. It's always going to be pointing right to left. And the question, in fact, says that it's going to be a uniform field. So the capital E is constant. That means that the F must be the same for both electrons as well. So now all we need to do is write down this answer. The field points from right to left, so positively charged particles would move right to left. That means that the negatively charged particles have to move left to right. Right? Negatively charged particles move in the opposite direction to positively charged particles, which means they move against the direction of the electric field. The strength of the force on a charged particle is the product of its charge and the electric field strength. And in a uniform field, and two particles with the same charge, the force will be exactly the same. Question 15. Classify each of the following as scalar or vector quantities, justifying your answer. A. Electric charge. Now, is this scalar or vector? Remember that scalar quantities can be represented by a number, but vector quantities have to be represented by a number and a direction. So in the case of electric charge, all we need is a number. So it's a scalar. It's either going to be a positive or negative number, and it does not have a direction. What about electric field? Can this be represented just by a positive or negative number? No, in a diagram we have to draw it with arrows. That means it must be a vector. So an electric field is a vector because it has both strength and a direction. It'll always point in the direction of that a positively charged particle will move, which means it points towards negatively charged particles and away from positively charged particles. So that's the end of the questions. In this section we've learned about electric fields, what they are and why we're useful. Electric fields are a very useful tool for thinking about electric charge and how it affects other electric charges.